All right, my friend, today we talk about a very important topic, which is what the heck is this binary deal? We left with a very good comprehension of what is a computer. Good, I mean a good model to work with this machine. We have basically a notepad in which I can write numbers and a calculator, or better, an arithmetic logic calculator that can perform arithmetic logical calculations on the numbers which are in the notepad. The notepad, of course, is the RAM, and the calculator is the ALU, which is inside the central processing unit. Basically, I have numbers that are processed by the CPU. Cool. So basically, I'm telling you that your fantastic MacBook is a calculator. Yeah, kinda. Yeah, we can really abstract our machine as a calculator and a piece of paper. But of course, this is an extraordinary simplification that will allow us to work with code very easily, okay? I told you last time that inside this notepad, inside the RAM, I can stock data. This data comes in the shape of integer or in the shape of real. Basically, integer are numbers which don't have a point, and real are numbers that have a point. Easy peasy. Real numbers are kind of tricky, and they're not really used on real code. So we're going to focus our attention in the integer data type, namely char, short, int, and long, to cover our fundamentals course, okay? I repeat to you from last time that reals are stocked inside my notepad in a qualitatively different way, respective to the integer types. All right, regarding my analogy of the computer made up of a simple calculator and a notepad, I want to show you this video. So this is from the channel Lex Friedman, which is an amazing channel, has all the amazing interviews with very interesting people. This time he's interviewing David Patterson, which is this fellow here, and he is very well known in the computer science ecosystem because he wrote this book, which is the gold standard for understanding what is inside a computer. Basically, when I tell you that a computer is just a calculator and a notepad, I'm collapsing the complexity of this book in few lines because we don't have that much time. It's like 1,000-page book. And by the way, it's not necessary to know all the bits of a computer. You just need some models to work as a programmer. If you want to be an electrical engineer or a really, really good software engineer, that's a very good idea to study all this stuff. Anyway, Patterson is the gold standard for architecture, and let's hear together a little piece of his interview with Lex.
Basic instructions and how did they change over the years? So we're talking about addition, subtraction. These are the
the specific. So the things that are in a calculator are in a computer. So any of the buttons that are in the calculator in a computer.
So have you heard what he just said? Every button which is inside a calculator is inside a computer. He's basically told us, all right, there is a calculator inside the computer. Cool.
So if there's a memory function key, and like I said, turns into putting something in memory is called a store, bringing something back is called load.
Just a quick tangent.
So when you talk about store and load, this strange word, is talking about take a number from the RAM, from the notepad, and bring it into the CPU, into the calculator. This is the load operation. Basically, take a number and bring it in the calculator. The store is the opposite. Take a number from the calculator and bring it into the RAM. Load and store, basically, piece of paper, calculator. I can take numbers from the piece of paper, the RAM, and bring into the calculator, and I can do the opposite. That's very abstractly what is going on, but that's basically it. Oh, now the key points that I want you to really listen carefully.
So that's memory and loads and stores. But the big thing, the difference between a computer and a calculator is that the computer can make decisions. And amazingly, decisions are as simple as, is this value less than 0, or is this value bigger than that value? So there's, and those instructions, which are called conditional branch instructions, is what give computers all its power. If you were in the early days of computing...
All right, I think we have seen enough. I will link this video in the description. Of course, watch it. If you find it interesting, of course, I suggest you to watch. And yeah, you have a calculator, a notepad. This calculator is different from a normal calculator because it can take decisions. That's all there is. You have a calculator that can take decision based on the values it is processing. All these operations are happening staggeringly fast. Namely, you have like for a 3 gigahertz central processing unit, you have 3 billion operations per second, 3 billion subtraction movement and stuff. So computers are arithmetic logic calculators that can take decisions really, really fast. Okay, we closed the argument of what is a computer. Our course on computer architecture is finished here. Of course, I repeat to you, read this book. It's really amazing. And another suggestion that I want to give to you is this one. There is a marvelous page on GitHub, which is GitHub free books. Okay, here you can find all the books related to computer science for free, and in all the languages. As you can see, you have English, but all the languages. We can say English by subject, and boom, here it comes. You have all the jazz here. For example, you see you want to search, I don't know, Patterson. There is not, but computer architecture. Here it comes. Computer organization and architecture, and here you have some good material. Okay, that was a tangent. Let's go back to the slides. So today we have to understand how this binary deal works. We have the number 42, and in binary it becomes 10, 10, 10. Why? How? How does it work? It seems very cryptic. You will see that it's not that difficult. It's just an easy mathematical trick. Okay, so we are gonna start our journey with this not funny joke, which is there are 10 types of people in this world, those who know binary and those who don't. This is the way a person who doesn't know binary would have read this joke. So if you understood this joke, basically you can abandon this video and skip it. But if you're not sure how this joke works, well, stay with me. To understand this joke on the marrow of our bones, which is what we are looking for in a fundamentals course, we have to start from far apart. We're going to start from the caveman, so from very, very far apart. So let's say we have 4 ducks, and I want to store this value in a piece of paper, okay? Or better, in a stone. How a caveman could have performed this task? Well, there are some methods, okay? We can decide to draw duck by duck. We can draw 4 ducks, and here it comes. I have stocked inside a piece of stone the value 4 in its most natural way. Namely, I have 4 ducks drawn inside my stone. Easy peasy. Well, you understand that this becomes really tedious really soon, given that, for example, if I have 300 ducks, good luck to log all these ducks inside a piece of stone, right? It's going to become super tedious immediately. So I need a better abstraction. I need a better model to store this value without wasting so much time. I can say, okay, 1 duck is equal to 1 line. So 1 duck, 1 line. I have 30 ducks is going to be 30 lines. But again, the problem arises even for this method, because if I have 300 ducks, it's going to be 300 lines. And good luck to read properly 300 lines. It's going to become immediately confusing and cumbersome. I need a better abstraction. I need a better method to store this value. Here we stumble into symbols. We have indeed created in all the history of humankind all kinds of symbols. For example, here we have the Roman numeral symbols. We have an XX, V, line. It means 27 in Roman numeral system. Basically, we have created some symbols that carry a specific value. For example, the symbol X is the value 10. The symbol V is the value 5. And then we have combined all these symbols into a single combination. This combination is carrying out a specific value. This is already a good abstraction. We can encapsulate big values into short symbols, into short combinations. Okay, so the Roman numerals are part of a numeral system, namely a method to display a specific value, thanks to some specific symbols. There is plenty of these numeral systems. For example, here I have the Babylonian numeral system and the Roman numeral system. But look here, for example, I'm on Wikipedia, list or numeral system. There is plenty of this way of encapsulating value. For example, we have the Egyptian numerals. As you can see, we have these really strange draws. The Babylonian numerals, which are these draws here. And frankly, there are lots of them. Many ones we don't know. As you can see, every numeral system has its own specific way of depicting value. This is our system. We have the Western Arabic numerals, Indo-Arabic numerals. As you can see, we have these specific symbols that for us are natural to see. We perceive immediately the value the symbols carry out. So you understand from this point that basically every civilization had its own proper way of encoding value inside a specific symbol. So you can derive a lesson from this point, that we have a difference between a symbol and a value. They're not the same thing. That's the takeaway from this point. So for example, the value 1 can be represented by this symbol, which is natural for us. For modern civilizations, the value 1 is represented by this line, but it can also be represented by this symbol here, or this symbol here, or this symbol here. You see? So you have different symbols like this one, or like this dot. So the value 1 can be represented by a plethora of symbols, and this is arbitrary. So it is decided, we get a consensus about what is the best symbol to represent a value, and we all agree on that. So take-home message, symbols are not values. We have symbols that represent a value that we decide. Okay, cool. So in this specific slide, I showed you that you can represent the value 5. You can represent 5 ducks with the letter V in the Roman numeral system, with these 5 calyx in the Babylonian system, with the symbol 5, namely the draw 5 in the Indo-Arabic system, the one we use. As you can see here, we have the 5 coming from the Chinese numerals, and then you have the string piat, which means 5, so 5 elements in Russian. Even a combination of characters is a symbol at the end of the day. You will understand immediately. Here I say to you this punchline: the value of a symbol is in the eye of the beholder. Basically, we have a plethora of symbols that can mean a specific value. We have this V that in Roman numeral system means 5, right? 5 elements. But this V can mean a lot of different things depending on the context, depending on how you decide to decipher this symbol, right? Remember this point, decipher this symbol. For example, Churchill, during the Second World War, to say to the people that everything was good, was correct, everything was fine, and soon we're gonna win this fucking war, he used to make this symbol, which was like that. This, of course, in this context meant victory. We're gonna win the war. But we understand this only by the context, because the symbol can mean victory, can mean 5, can mean 2, the value 2, can mean an arrow toward the bottom, or can mean, I don't know, everything is fine, okay? There is a really an endless list of deciphering of meaning that this symbol can have, depending on the way you want to decipher this symbol. So pay attention to this word, gift. In your mind, immediately you think, gift, oh, this is cool, this is a good word. But because you decipher this word in English it means something cool. It means that someone is giving you something for free, and this is a good news. But if you decide to decipher this series of characters, this series of symbols into German, well, you get a very different result. You get a very different value. Gift means poison in German. So keep this idea in mind, that you have the same symbol, G-I-F-T, can mean a gift, indeed, or can mean poison, depending on how you decide to decipher. Cool, we are ready to go on. So we have our system, which is the base 10 system. What does it mean? What does it mean, base 10? As you can see from the math definition, base is defined as a set of digits used to represent numbers. Different number systems use different combinations of digits as the base. For example, the binary number system uses only 2 digits, namely 0 and 1 to represent numbers. The octal numeral system, which is used in computer science, uses 8 digits. Namely, we have from 0 to 7, namely 8 digits, hence base 8, to represent numbers, and so on. The most common number system that we use is the decimal number system that uses the base 10, which includes digits from 0 to 9 to writing numbers. It's the system we use on a daily basis. Okay, so for a base definition, we have this one, which is the best. Base in math is defined as the total count of digits used to express numbers in a number system. That's perfect. That's exactly what a base is. So in our system, we have these 10 digits, these 10 symbols that, as you can see, are not totally arbitrary. You see the number 1, the draw 1 has 1 angle, the number 2, 2 angles, the number 3, 3 angles, and so forth. Basically, every symbol, every draw carries a specific value, and this value is given by the angles. Now, we perceive these symbols as almost natural, almost like these numbers are out there in reality, and you don't perceive this like a simple abstraction made by humans to encode values, right? When you see 1, 0, your mind is immediately thinking about 10 stuff, 10 ducks, 10 elements. because we are so tailored to this base that we don't even think about other base systems, right? It is almost a second nature for us because we have been exposed since the beginning to this base system, all right? So you understood that there are different bases. For example, you see the page of before, list of numeral systems. So you see here, all the numeral systems have their specific base value, namely the number of digits that I can use to encode values. You see here, you have the Egyptian numerals, base 10, allegedly. Babylonian numerals, it's base 60, I know. By the way, it is why we have 60 minutes in an hour and 60 seconds in a minute. This comes back to the Babylonian numeral system. And you may wonder why a 60 base system? Well, I will explain you now. First of all, why we do use this base 10 system, why we need 10 symbols to encode a value. Well, you may ask yourself, where do these digits come from? Well, the answer is in the question itself, because these symbols come from the digits. Indeed, we have 10 symbols because we have 10 fingers. So we use a base 10 because we have 10 digits. We have 10 fingers. Basically, when we count stuff, we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all right? We use these tools, we use these little sticks to encode some values, right? That's why we have a base 10 system. So in a base 10, you know that we have symbols that range from 0 to 9, right? Namely 10 symbols. So let's try very stupidly to count 10 elements in our base system. What do we do? Remember that we have 10 symbols from 0 to 9. When we have finished these symbols, what do we do? Well, very simply, we add 1 to the upper level because we are dealing with positional numbers. This is like super basic arithmetic. So let's start. I start 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't have any more symbols, right, to encode a value. What do? Well, I increase by 1 the upper position. 10, 1, 0. Cool. That's the way by which I count 10 ducks in a base 10 system, our base. That's so simple, that's so natural that we don't even think about that, but this is the way it works. But let's pretend now that we were not old sapiens, but we were Mickey Mouses strolling around. Well, if we were Mickey Mouses, we had only 4 digits. Namely, we had only 4 digits per end. So if I want to count 10 ducks being a Mickey Mouse, how can I do? Well, probably we would have came up with a base 8 system. Why 8? Well, because we have 8 fingers, right? So from 0 to 7. And then I simply start to count, right? As a Mickey Mouse. 0, 1, 2, 3, 4, 5, 6, 7. That's my last symbol. So what do? 1, 0. 1, 0. Okay, what is this 1, 0? I increased by 1 the upper position. But this time it's not 10 ducks, right? It's not 10 elements. It's going to be 8 ducks. If I want to count 10 ducks in a base 8, like a Mickey Mouse, the number would be 1 and 2. Okay, you get 1, 2, 12, you would read that, but it is not a 12, it is a 10. I know it's kind of tricky to understand, but it is the way it works. So, to recap, 10 ducks in a base 10 system are 1, 0, that symbol. That for us is almost natural to think about 10 elements, 10 ducks. In base 8, namely, if we were all Mickey Mouses, the number 10 would have been 1, 2. Why 1, 2? I told you. I have 8 fingers. 1, 2, 3, 4, 5, 6, 7. I finished my symbols. I increase by 1 the upper position and I restart, like a normal numbers in base 10. So I am at 8, 9, 10. The number is 1, 2. 1, 2 in base 8 is the number 10. Okay, cool. We are going on. Now we stumble upon the binary symbols. Let's pretend we are not Mickey Mouses, but we are dolphins. So we have only 2 fingers, namely 2 fins. We have 1 and 2 fins. Cool. So we have only 2 symbols. We have the 0 and the 1. Now, how can I count, for example, 10 elements with only these 2 symbols? Can I do that? Well, of course I can. It is tedious, but I can. So let's try to count initially 2 ducks. How do I do? Well, I told you I have only 2 symbols, base 2, 0 and 1. So let's try to count 2 ducks in a binary system, being a dolphin. I have only 2 symbols, 0 and 1. So we start. I have 0, 1. I already finished all my symbols. So what do? I increase by 1 the upper position. So 2 ducks are gonna be 1 and 0, right? Like a normal number, you understand what is going on. If I want to count 10 ducks, it's gonna be super tedious because I have 0, 1, I increase the upper position and I restart. 0, 1, I increase the upper position, but this one is already at the maximum, so it's gonna be super tedious. We are not gonna do. I hope you get the point by now of what is going on. So by the way, if you want to further more your knowledge about this topic, I highly suggest this book, which is Code. Code, the hidden language of computer hardware and software. This is amazing. This is the best book to understand all that I've been explaining to you till now. I highly suggest. So you're smart enough to find your source, and we keep going on. So we are here. We have a binary system, and that's exactly what is inside our computer. We have a binary system. For a dolphin, a computer, a binary system is totally normal. It's totally fine. It is not a leap. It's just the way things work inside his brain. We unfortunately have this base 10 very settled inside our brain, so it's kind of difficult to understand that there are other base systems. By the way, I was telling you that the Babylonians have a base system of 60, and why did they have this base system? Well, think about that. We have this phalanx, and we have 12 of them, right? We have 1 2 3 4 5 6 7 8 9 10 11 12. So what can I do? I can, with my thumb, count here. So I have 1 2 3 4 5 12, and then I say, okay, 12 per 1 field, and then I can keep going on, 13, 14, 15, 16, so 24, I keep increasing here, till I arrive to fill my left hand, 5. So I have 5 per 12, I get 60, because they counted in this fashion. That's why they had a base 60. I think this is pretty legit, this is pretty intelligent. So at the end of the day, these base systems were tailored for humans to count stuff. Okay, this binary system is tailored for computers. But at the end of the day, that's the same idea, that's the same logic. If we have a binary number or a number in base 10, or we have an hexadecimal number that is a number in base 16, which is used in computer, we are still dealing with numbers. We are still dealing with values. The only thing that changes is the representation method, is the symbol that is representing this value. But in my mind, it's only a number. And this is important. So how does it work? We have the number in base 10, 42. How do I count? How do I count the value which is stocked inside the symbol? Well, if this is in base 10, 42 is equal to 2 per 1, because the 2 is in the position of the ones. The numbers are indeed positionals. So I make 2 per 1 is equal to 2, and the 4 is in the 10th position, so I have to make 4 per 10. 40 plus 2 is equal to 42, because we are in a base 10, so every position is 10 more respective the previous. This is almost trivial for us, right? We are so accustomed to base 10 that this is a second nature. How about binaries? Well, in binaries we have a base 2 symbols, so every position is the double of the previous, and that's the idea behind the binaries. So we have 1 per 0 0, 1 per 2 2, 4 per 0 0, 1 per 8 8. Basically I go to sum all the numbers that have a 1, so I have 32 plus 8 plus 2 is equal to 42. So the binary representation of the value 42 is 10 10 10, but 42 base 10 and 10 10 10 base 2 are the same value. The only thing that changes is the base representation, is the language in which I want to encode the value. It's like saying gift, padarak, regalo. They are the same word. They are gift in all the languages. They encode the same idea. It is like the base is the language by which I want to decode a specific symbol. For example, if I say hello, ciao, привет, salut, all of these symbols convey the same meaning, right? The meaning of hello. I need a specific key and a specific language to decipher the meaning, but the meaning is always the same. Well, you can think that the base is practically the same thing. You have a symbol and you have a specific key, a specific base to decipher the value which is inside this symbol. Okay, now I want to show you on the slide. As you can see, we have the binary representation of 42, which is 10 10 10. This is a base 2 system because we have 2 symbols. Then I have 0x42. When we have 0x as a prefix, this is an hexadecimal value. You will learn very soon what is an hexadecimal value. You may recall that we use hexadecimals to represent byte addresses. You remember from the first lesson. You see all the bytes have a specific address, and this address is written in this very strange way. This is an hexadecimal number, and it is very cozy to encapsulate a lot of value with few symbols. Anyway, here I have an hexadecimal number, which is 0x42, and then I have a normal decimal number, which is 42. So what is the value of this 0x42? Well, this is not the value like in decimal 42, because I repeat to you, we have a 16 decimal base. So we have 2 per 1, which is in the first position, and then in the upper position we have 4 per 16 and not 4 per 10, because this is an hexadecimal base. So we have 64 plus 2. So this 0x42 is the value 66. It is 66 things, okay? As you can see, it is the same symbol as 42, right? In base 10. 42, 42. If you see like that, your brain is telling you, okay, this is a 42 stuff, 42 docs, but this is not. Do you remember my slide here? I told you that gift has very different meaning depending on the language you want to decipher this series of characters. That's exactly the same idea. Here we have two things which are equal if I watch like that, right? I have 42 and 42, but they are not equal at all. The hexadecimal number, the blue one, I want to decipher with a base 16, while the green I want to decipher as a base 10. So they convey a very different meaning. It's like deciphering gift in German and deciphering gift in English. Different total stuff. So if I want 42 in hexadecimal, what is the real number? Well, it is this number here. It is the number 2a, you see? You see a letter here, strange. For a number, you have a letter. Yeah, because this is a convention, I repeat to you. We decide, as humans, which are these symbols. For our base 10 symbols, we have these 1, 2, 3, 4, 5 symbols that have angles that carries out the specific value, but we can have all the symbols we want. It is something that we decide. So we decided that the value 10 is represented by the letter A in hexadecimals, value 11, the letter B, and so forth, till the F, which is the last symbol in my hexadecimal system. Okay? All right. This is, in my opinion, a difficult topic to understand all these base deal if you stumbled upon for the first time into these ideas. So I really suggest you to read this book that I told you before. With this book I managed to digest all these base system deal, and it was tough initially for me to understand. And yeah, if you read at least the first part of the book, you are already on a good position. All right, now it's time to show you something more practical, okay? I'm gonna show you a code that is gonna take a value and convert this value into a specific base. I recall to you that a base is just a set of symbols that encode a value. So here we come. I have a program that is able to convert whichever value in a specific base. As you can see, it's pretty longish. You definitely should not understand what is written here. Otherwise, there is no meaning on you watching this video. But you will very soon be able to write code like that. My goal is to bring you from nothing to being able to do what I do, and I'm really striving for that. So let's run this code. I have the value 42, namely 42 things, 42 elements, and I want to write this number in base 2, which is composed by two symbols, right? From 0 and 1. Let's see what we get. Well, you get this number, which is 10, 10, 10. You know perfectly well, this is the ones, this is the twos, this is the fours, this is the eights, and so forth. So we have 32 plus 8 is equal to 40 plus 2 is equal to 42. Perfect. But we can have a base 2 with all the symbols that we want. For example, I can have 42 with the symbols comma and point. Look carefully now. Boom. You see here. This very strange symbol, combination of symbols better, is the value 42. In the base system, comma point. The comma point base system is composed of two symbols. So this is a base 2 system. As you can see, it is specular to the 10, 10, 10. Just pretend that the 1 is the point and the 0 is the comma. You will see that it's exactly the same. It follows the same rules. So we really don't care about which symbols we are using. We care about the positional value of the numbers. Okay, so the comma carries out the value 0 and the point carries out the value 1. So we have here 1, 1, and 1. In which position? In 1, 2, 4, 8, 16, 32. That's the same idea as before, because we have a binary system. So I have 1, 2, 4. Every position is the double of the previous, but the first one, which is 1, right? Okay, this is kind of tricky to understand, but I think you start to grasp this concept. Now let's do 42 in base 4. in base 4, so I have my 4 symbols, which are 0, 1, 2, 3. What is that? Well, is the 2, 2, 2. You see? 2, 2, 2 is the value 42 in base 4. Okay? Why is that? Well, because you have 1, 4, and then 16. So we have 2 plus 4 per 2 is equal to 8 plus 2 per 16, 32. 32 plus 8 plus 2. Okay, is equal to 42. Cool. Let's do 42 in base. What base is that? I think you know pretty well. Well, this is, my friend, the base 10 that we use in Arabic symbols. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Boom. What do we get? 42, of course. The value 42 in a base 10 is 42, is the number itself. Now we're going to do in base 16. Namely, I have 16 symbols, and we're going to see what value we're going to get. 2a. Do you remember? That's exactly the value I was telling you. 2a. This symbol encodes the value 42. Perfect. So what we do really care is the binary representation of numbers, because that's what is gonna end up inside my RAM. Why? Well, I told you in the first video, my RAM is just a series of bytes. A byte is composed of 8 bits. 1 bit is just one little bulb that can be turned on and off. So this on and off means 1 when on or 0 when off. Okay, so I can write numbers exploiting the electrical state of these bulbs. Okay, I can turn on, off 6 bulbs, and this number is gonna be 42, as you can see from here, right? Just look at the first line. I'm gonna turn on these 3 bulbs, and in my mind, this is the number 42. This is 42. It's like when I write int nab is equal to 42, in some place in memory, I turn on and off these little bulbs. This is the binary representation of the value 42. Why in binary? Well, because I'm working with this machine. It is a machine that can only store this kind of data because it's made up of little bulbs. We are exploiting the way this machine is built. So that's the idea of binary. Now you might say, well, very cool, but how I can start from a decimal value and convert it to a binary? Now I'm going to show you the algorithm we use when we want to convert a decimal number into its binary configuration. So this is the algorithm. Of course, you should not understand what is going on, but just maybe give a first glance of what is a code, what is a program. That's it. This is a program in C, and this one specifically is gonna convert a number in base 10 in a specific base. In this case, I have base 16, but let's make base 2, okay? All right, so I'm gonna compile this code. I will explain you this concept of compiling, of course. Okay, I compile. Basically, it means translate for the computer this code. And then I'm gonna launch the program. Boom. Look carefully now. I have this number, which is the number 42. As you can see from here, right? I have the number 42 and the base, which is the base 2. I take the number, I divide this number per 2. As you can see, I have the slash, which means division, and I get a reminder, okay? This reminder, 42 divided by 2 is equal to 0, of course. Then I take the result of this first division and I get 21. 21 divided by 2 is equal to 10, of course, with the reminder of 1 this time, okay? I do the same operation here, 10 divided by 2 with the reminder here. I get 5, 5 divided by 2, reminder by 1, and so forth. When I get 1 divided by 2 is equal to 0 with the reminder of 1. So here, my algorithm is gonna finish. Do you see something familiar here? Well, just read the reminders from bottom to top. Look here, I have 1, 0, 1, 0, 1, 0. What is that, my friend? Well, I think by now you know very well this number. It is the number 10101042, right? So I think that at the moment I don't recall exactly what is the name of this algorithm. I think that it is the subsequent division algorithm or the or something like that, but never mind the name. Nomenclature is not important. The important is the idea. So you take a number, you continuously divide by 2 because we are dealing with a base 2, and you take the reminder. Then you read from the bottom up these reminders, and here it comes. This is your number. Let's try another example. This time we are gonna make the number 1337 still in base 2. I compile and I launch my program. This time is a bit longer, but the same idea. I start from the top, so I get this very long series of reminders, 101001. This is the binary configuration of 1337. Let's change the base this time. Base 10, okay? What is going to happen in your opinion? Look at that. What do I get? I get the number 1337. Of course, this is already in base 10, so doing this algorithm is gonna give me back the exact same number. Okay, one last thing, I want to make this in base 16, compile and run. Look here, I have 539, which is not telling me the point I wanted to make, but let's make the number 42. Okay, I recompile and then I run. Look here, I have 42 divided 16 and 2 divided 16, I get 2 and 10. Now in hexadecimal, as I was telling you, hexadecimal symbols. Okay, in hexadecimal base, we have these specific symbols. Is here. Now it's kind of pixelated. Let's find something better, like this one. Okay, so I have my decimal value, as you can see here. The hexadecimal are equal to the base 10 till the 9, but then I have A, B, C, D, A, F. A is equal to 10, B is equal to 11, C is equal to 12. So here, this 10 here, if I want to write this number properly in hexadecimal, should be A. A because in hexadecimal carries out the value 10. And I repeat to you, this is a total convention. A is a simple letter. It's cozy to use a letter that we all know. We could have put there, I don't know, whichever symbol come to your mind. So this lesson has been kind of tricky. You need to make your research to digest this material, I think, but TLDR, we can stock inside our computer numbers. These numbers are in binary because our physical RAM is made up of binary elements, namely light bulbs, namely transistors. So we need to encode values in this configuration. Even though as a programmer, I can perceive these as simple numbers. I don't really care that they are written in binary, and for me, it's just a mental masturbation. But you will see that knowing this thing will pay its dividends in the long run, because once you start to write more and more complex programs, you have to understand what is going on underneath the hood. I'm talking about the overflow problem that you will know very soon. So to sum it up, I have my arithmetic logic calculator, my notepad. Inside my notepad, I can write numbers, which are in binary, and with my arithmetic logic calculator, I can perform arithmetic logic operation. Okay, that's it for this video. In the next one, we're gonna start to perform operation on these strange binary numbers. All right, thank you for watching, my friend. Enjoy.